Planetary rings are not decorations. They are not cosmic ornaments placed around planets for aesthetic effect. They are the aftermath of violence. Every major ring system in our solar system formed because something was torn apart. To understand how Earth could have rings, we first need to understand the fundamental rule that governs their existence: the Roche limit. The Roche limit is the minimum distance at which a large object held together by its own gravity can orbit a planet without being pulled apart by tidal forces. Tidal forces are differences in gravity across an object. If a moon or asteroid orbits too close to a planet, the side closer to the planet feels stronger gravitational pull than the far side. That difference stretches the object. If it crosses a critical threshold, the object cannot hold itself together. It fractures. It shatters. It becomes debris. For Earth, the Roche limit depends on density. For a rocky body similar in density to our moon, the Roche limit would be roughly 18,000 to 20,000 kilometers from Earth's center. Inside that boundary, a moon-sized object would begin to break apart under tidal stress. The result would not be an explosion. It would be progressive fragmentation. Large chunks would separate first, then smaller ones. Over time, the fragments would collide with each other, grinding down into smaller particles. The system would evolve into a flattened disk of ice and rock orbiting along Earth's equatorial plane. That flattening happens because of angular momentum conservation and collisions. When debris orbits a planet, particles interact. Collisions dissipate vertical motion. Over time, the debris spreads into a thin, stable ring aligned with the planet's rotation. This is why Saturn's rings are so flat. They are only about 10 meters thick in some regions, despite spanning hundreds of thousands of kilometers in width. Rings are not solid structures. They are countless independent particles, from microscopic dust grains to house-sized boulders, all orbiting under gravity. There are several ways rings can form. One is tidal disruption of a moon that migrates inward past the Roche limit. Another is a massive impact event. If a large asteroid strikes a planet and ejects enough material into orbit, that debris can temporarily form a ring system. A third possibility is capture and fragmentation of a passing object that wanders too close. In Earth's early history, violent collisions were common. In fact, the leading theory for the moon's formation involves a Mars-sized body colliding with early Earth. That impact ejected massive amounts of material into orbit. For a period of time, Earth likely had a temporary ring system before the debris coalesced into the moon. So Earth having rings is not fantasy. It may have already happened. The difference between a temporary debris disk and a long-lasting ring system depends on one factor: orbital distance. If the debris remains outside the Roche limit, gravity allows it to clump together and form moons. If it remains inside the Roche limit, it cannot reassemble. It stays as rings. Rings are not stable forever. Over millions of years, gravitational interactions, atmospheric drag, and radiation pressure cause them to spread or decay. But for long periods, millions to potentially tens of millions of years, they can persist as massive orbital structures. Planetary rings are not magical. They are the delicate balance between gravity pulling inward, orbital motion pulling outward, and tidal forces tearing objects apart. They exist where moons fail, and if Earth had them, it would mean something once tried to become a moon and didn't survive. Earth having rings is not impossible. It is improbable today, but entirely plausible in the past. To understand whether Earth could realistically have rings, we need to look at its history. The early solar system was violent. Planets did not form peacefully. They collided, merged, shattered, and reassembled over tens of millions of years. About 4.5 billion years ago, a Mars-sized body known as Theia is believed to have collided with the early Earth. That impact was not a glancing hit, it was catastrophic. The collision vaporized rock, melted crust, and ejected enormous amounts of debris into orbit. For a period of time after that impact, Earth was surrounded by a thick disk of molten rock and vaporized material. That disk was effectively a ring system. The reason it did not remain a ring is because much of that material orbited outside Earth's Roche limit. Gravity allowed it to clump together. Over time, it coalesced into the Moon. If the debris had remained slightly closer to Earth, inside the Roche limit, it would not have formed a moon. It would have stayed fragmented. Earth would have kept its rings. So the difference between "we have a moon" and "we have rings" may have been orbital distance. Now imagine a different scenario. Suppose Earth once had a second, smaller moon. Over millions of years, tidal forces could cause that moon's orbit to decay. If it drifted inward past the Roche limit, tidal stress would begin tearing it apart. Not instantly, but progressively. Chunks would break away. Collisions would grind those chunks into smaller fragments. Eventually, the entire moon could become a debris field orbiting Earth's equator. That debris would flatten into rings. This is not science fiction. Saturn's rings are likely the remains of one or more destroyed moons. Another possibility involves asteroid capture. If a large asteroid passed close enough to Earth and was gravitationally captured into orbit, its trajectory might decay. If it crossed the Roche limit, it would fragment into a ring system. There is also the possibility of a large impact ejecting enough crustal material into orbit to form temporary rings. Some models suggest that even relatively late impacts in Earth's history could have created short-lived debris disks. But today, the conditions are different. Earth has a large moon that stabilizes its gravitational environment. The moon's presence makes additional large satellites less stable. Gravitational interactions would disturb any long-term ring formation unless the debris stayed strictly within the Roche limit. There is also atmospheric drag. Earth's upper atmosphere extends hundreds of kilometers into space. Very low-orbit debris experiences slight drag over long timescales. Small particles in low rings would gradually spiral inward. For Earth to maintain a long-lasting ring system today, the debris would need to orbit high enough to avoid significant atmospheric drag, but low enough to remain inside the Roche limit. That is a narrow band. So could Earth realistically have rings? Yes, especially in its early history. Does Earth likely have rings now? No, but the physics does not forbid it. In fact, the existence of the moon suggests that Earth once came very close to being a ringed planet. One slight difference in orbital evolution, one slightly different collision geometry, and instead of a moon rising over the horizon, we might have seen a luminous arc stretching permanently across the sky. If Earth had rings, the next question is scale. Because when people imagine rings, they usually imagine something thin and decorative, a faint halo, a subtle band. That is not how real planetary rings work. Let's use Saturn as a reference point. Saturn's rings extend up to about 280,000 kilometers across in diameter. That is more than 7 times the diameter of Earth. Yet despite that immense width, the rings are incredibly thin. In many regions, they are only about 10 to 100 meters thick, a structure wider than most continents, thinner than a skyscraper is tall. If Earth developed rings, their size would depend on how much material was available and where it orbited. The inner boundary of the rings would likely sit just above Earth's atmosphere, low enough to stay within the Roche limit, but high enough to avoid significant atmospheric drag. The outer boundary would extend to the Roche limit itself, roughly 18,000 to 20,000 kilometers from Earth's center for rocky material. Since Earth's radius is about 6,371 kilometers, that means rings could span from perhaps 8,000 to 10,000 kilometers above the surface outward to nearly 14,000 kilometers above the surface. That creates a ring system tens of thousands of kilometers wide. From space, Earth would resemble a scaled-down Saturn, a bright disk encircling the equator, perfectly aligned with the planet's rotational axis. Now consider mass. Saturn's rings are surprisingly light compared to the planet, about the mass of a small moon. Earth's rings would likely be far less massive unless a very large moon was destroyed. If a small lunar fragment or captured asteroid was torn apart, the total mass of the rings might be equivalent to a medium-sized mountain spread out over thousands of kilometers. That sounds small, but distributed in orbit, even a modest mass creates dramatic visual impact. Brightness would depend on composition. If the rings were composed of icy material like Saturn's, they would be highly reflective. If composed mostly of rocky debris, they would be darker and more muted. Given Earth's proximity to the Sun and lack of abundant surface ice in orbit, Earth's rings would likely be rock-dominated. That means they would not glow white like Saturn's rings. They would appear gray, dusty, and metallic, still bright enough to reflect sunlight, still large enough to dominate the sky. Thickness would remain minimal. Collisions between particles naturally flatten ring systems into thin disks. Vertical motion dissipates over time. Even a ring only 50 meters thick, if spread over tens of thousands of kilometers, becomes visually overwhelming. From the surface, the rings would not appear as a narrow line. They would appear as a massive band stretching horizon to horizon, depending on latitude. And the apparent width in the sky would vary dramatically based on your position on Earth. At the equator, the rings would pass directly overhead. At mid-latitudes, they would appear angled, slicing diagonally across the sky. At the poles, they might appear as a thin glowing ring near the horizon, or nearly vanish depending on geometry. The key realization is this: Earth's rings would not need to be as massive as Saturn's to be breathtaking. Even a relatively modest debris disk confined within Earth's Roche limit would create one of the most visually dominant features imaginable in the sky. Not a faint arc, but a permanent planetary scale structure hovering above the equator, visible every day for millions of years. If Earth had rings, their physical dimensions would be extreme compared to anything we are used to thinking about. The inner edge of the ring system would likely begin several thousand kilometers above the surface. It could not sit too low because atmospheric drag would slowly pull particles downward. But it also could not extend too far outward because beyond a certain distance, debris would begin clumping into moons instead of remaining as rings. For rocky material around Earth, the Roche limit would sit at roughly 18,000 to 20,000 kilometers from Earth's center. Since Earth's radius is about 6,371 kilometers, that means the outer boundary of the rings could extend roughly 12,000 to 14,000 kilometers above the surface. That is nearly twice the altitude of geostationary satellites. So from the ground, the rings would not appear like a thin halo. They would span tens of thousands of kilometers in width. From space, Earth would look dramatically different, a solid sphere surrounded by a vast, flat disk stretching outward far beyond the planet itself. And yet, despite that massive width, the rings would be incredibly thin. Real ring systems flatten naturally due to collisions. Particles bump into each other. Vertical motion gets dampened. Over time, everything settles into a thin plane aligned with the planet's equator. Even if Earth's rings were only 50 to 100 meters thick, they could stretch across 20,000 kilometers in diameter. That is like laying a sheet of material thinner than a football field's length across a structure wider than the United States. Now consider what that means visually. At the equator, the rings would pass directly overhead. Their apparent width in the sky would be immense, potentially spanning a large fraction of the visible sky dome. You would not see a narrow stripe. You would see a luminous band stretching from horizon to horizon. At mid-latitudes, the rings would appear tilted. They would cut diagonally across the sky, rising in one direction and sinking in the other. At the poles, you would see the rings edge on. They might appear as a thin, bright line circling the horizon, or barely visible depending on lighting conditions. The thickness of the rings would not dominate the visual experience. Their width would, even if composed of dark rocky debris rather than bright ice. Sunlight reflecting off millions of orbiting particles would create a visible glow. Earth's sky would never be empty again. It would always contain a planetary-scale structure arching overhead, a reminder that something once tried to become a moon and instead became a ring. If Earth had rings, the most dramatic visual difference would appear at the equator, because rings always align with a planet's equatorial plane. That means if you stood anywhere along Earth's equator, the rings would pass directly overhead, not slightly angled, not near the horizon. Directly above you. Imagine looking straight up at night. Instead of open sky filled with stars, you see a massive luminous band stretching from one horizon to the other. It would cut the sky into two halves, and it would not be small. Depending on the width of the ring system, it could occupy a large portion of the sky dome, possibly tens of degrees across. For comparison, the moon appears about half a degree wide. The ring system could appear dozens of times wider than that. It would look like a permanent celestial bridge. During the day, sunlight would strike the ring particles. If they were made of ice, they would shine brilliantly white. If rocky, they would glow more softly, silver gray with subtle brightness. But they would still reflect enough light to be visible even under daylight conditions. At sunset and sunrise, the effect would be even more dramatic. The rings would catch low-angle sunlight and glow intensely while the rest of the sky darkens. You would see a bright arc suspended above a dimming horizon. At night, they would reflect sunlight from beyond the horizon. Even when the sun has set for you, parts of the ring system farther west or east would still be illuminated. True darkness would become rare. Stars directly behind the rings would be partially obscured. Instead of a clean star field, you would see a textured, glowing band with subtle structure, gaps, density variations, maybe even faint divisions similar to Saturn's Cassini division. Weather would not hide them permanently. Even through clouds, you might see diffuse brightness filtering through. The rings would move slowly across the sky throughout the year due to Earth's orbit around the sun and axial tilt. But they would never rise or set in the traditional sense. They are locked to the planet's rotation. For people living near the equator, the rings would become part of identity. Every culture, every mythology, every calendar would be shaped by that permanent structure in the sky. There would never be a night where the sky feels empty. Instead of one moon that waxes and wanes, you would have an immense, continuous celestial band dominating your view of the universe. The equator would not just be a line on a map. It would be the place where Earth's rings own the sky. If you moved away from the equator, the rings would change dramatically. They would no longer sit directly overhead. Instead, they would begin to tilt. Because rings lie flat along the equatorial plane, your latitude determines your viewing angle. The farther north or south you travel, the more you see the rings from the side. At 30 degrees latitude, the rings would appear angled across the sky. They would rise from one horizon, arc upward, and descend toward the opposite side. Not straight overhead anymore, but still massive. At 45 degrees latitude, the tilt becomes more pronounced. The ring band would no longer dominate the center of the sky. It would hover at an angle, cutting diagonally across your view like a cosmic highway suspended in space. The apparent width would shrink slightly as your perspective shifts. You are no longer looking at the full face of the ring system. You are seeing it from the side, but it would still be immense. Imagine standing in New York, Paris, Beijing, anywhere in mid-latitudes, and seeing a permanent celestial structure spanning from northwest to southeast across the sky. It would be bright enough to notice even in twilight. At night, the stars behind the rings would dim where the band crosses. You would see structure in the ring itself, subtle brightness variations where particle density changes. Cloud cover would sometimes obscure it, but whenever the sky cleared, it would return. Predictable, immovable, always in the same orientation. As seasons change, the tilt would subtly shift due to Earth's axial tilt of 23.5 degrees. The angle of sunlight hitting the rings would vary. Some months, they would glow brighter. Other months, they might appear thinner as illumination changes. Now consider aircraft flight paths. Commercial planes cruising at 10 kilometers altitude would still be far below the rings. But visually, passengers would see them more sharply defined above the atmosphere's haze. Satellites in low Earth orbit would face risk if they crossed the ring plane. Any object intersecting that thin disk would risk collision with high-speed debris. But from the ground, the rings would not feel dangerous. They would feel monumental. Mid-latitude cities would live under a tilted celestial structure, permanent and unmoving relative to the planet. Every sunrise and sunset would interact with that arc. Light would scatter differently. The sky would never look the same as it does today. The further you travel from the equator, the less dominant the rings become. But they would still own a significant portion of the sky. A reminder that Earth is no longer just a sphere under open space. It is a ringed world. At the poles, the rings would almost disappear, because at the north and south poles, you are standing directly above or below the equatorial plane, and the rings lie exactly in that plane. That means you would see them edge on. Instead of a massive glowing band stretching across the sky, you would see a thin, sharp line circling the horizon, a faint ring of light skimming the edge of your vision. And in some lighting conditions, you might barely see them at all. From the pole, the full width of the rings collapses into a razor-thin line. All that massive structure, tens of thousands of kilometers wide, compressed into something that might appear no thicker than a distant contrail. During the day, sunlight would hit the rings at a shallow angle. Depending on the season, they might cast faint circular glows around the horizon. In winter darkness at the poles, the rings might glow faintly if illuminated by sunlight from beyond the horizon. But compared to equatorial regions, the visual dominance is minimal. There would be no arch overhead, no celestial bridge, just a luminous line circling the world. However, there is something subtle and powerful about that. At the poles, the rings would create a permanent horizon feature, a perfect geometric circle marking the boundary between Earth and space. Even in total darkness, if illuminated by distant sunlight, that line might shimmer faintly. The poles already experience extreme light cycles, months of daylight and months of darkness. With rings present, those long polar nights would include a thin glowing circle in the sky, a reminder of the planet's altered structure. Astronomers near the poles would have the clearest sky for observing beyond the rings. Since you are viewing the ring system edge on, it blocks far less of the sky compared to equatorial regions. But satellites orbiting in polar trajectories would face challenges. Many satellites use polar orbits to scan the entire planet. If the ring plane intersects those paths, collision risks increase significantly. For people living at the poles, the rings would feel distant and subtle. For people near the equator, they would feel overwhelming. The same structure, radically different experiences depending on where you stand. A ringed Earth would not look the same everywhere. It would reshape the sky differently for every latitude on the planet. Nights would never be truly dark again. Right now, when the sun sets, the only major source of natural light is the moon. And even the moon only reflects about 12% of the sunlight that hits it. On a full moon night, the landscape glows faintly silver. On a new moon, darkness dominates. With rings, that balance changes completely. A ring system contains millions, possibly billions, of particles orbiting Earth. Each one reflects sunlight. Even if the particles are rocky and darker than ice, the total reflective surface area is enormous. That means when the sun sets for you, parts of the rings farther west are still illuminated. Imagine the sun dipping below the horizon, but the massive band across the sky continues to glow. The upper portion remains lit by sunlight that hasn't yet set at higher altitudes and longitudes. The result would be a persistent twilight. In equatorial regions, where the rings pass overhead, The sky might retain a faint silver or copper glow for hours after sunset. You could read outdoors without artificial light on many nights. True pitch-black darkness, the kind required to see the faintest stars, would become rare near the equator. The brightness would vary depending on ring composition. If the rings were rich in ice, like Saturn's, nights could become dramatically brighter. If composed mostly of rocky debris, they would be dimmer, more like a permanent faint Milky Way band, but much thicker and more structured. There is another factor. The rings would also reflect Earth light. Just as the moon shines faintly from reflected Earth light during crescent phases, ring particles would reflect light bouncing off Earth's surface and atmosphere. That adds another subtle source of illumination. Over time, ecosystems would adapt to this brighter night environment. Nocturnal animals rely on darkness for hunting and protection. Increased night brightness would change predator-prey relationships. Some species might struggle, others might thrive. Human astronomy would suffer. Deep sky observations required dark skies. A permanent luminous band across the equator would block significant portions of the sky. Observatories would likely move closer to the poles where the rings are seen edge-on and interfere less. Culturally, night would feel different. Instead of a sky that fades into emptiness, there would always be structure. Always a celestial presence. A constant reminder of orbital debris encircling the planet. Nights would not disappear. But they would never be as dark as they once were. A ringed Earth would glow long after the sun is gone. The most powerful effect of Earth's rings would not be visual. It would be shadow. A ring system is not transparent. Even if made of countless small particles, their combined density would block part of the sun's light. And because rings lie in the equatorial plane, their shadow would fall in a predictable band around the planet. Imagine a permanent moving stripe of partial darkness circling Earth. During certain times of the year, especially near the equinoxes when the sun aligns closely with the equatorial plane, the rings would cast their widest and most defined shadow. Regions near the equator could experience measurable reductions in solar radiation, not full darkness, but a constant dimming. Think of it like living under a giant orbital sunshade. Depending on ring density, sunlight at the equator could be reduced by several percent. That might sound small, but climate systems are extremely sensitive to even slight changes in incoming energy. A 1 to 2% drop in solar input sustained over decades can influence global temperature patterns. Now imagine that reduction focused along a narrow latitudinal belt. Equatorial regions, which today receive the most direct solar energy, would experience partial shading. Surface temperatures could drop relative to present-day norms. Rainfall patterns would shift. The intertropical convergence zone, the band of heavy rainfall near the equator, might weaken or move. Monsoon systems could reorganize. Agriculture in equatorial nations would need to adapt to lower light intensity and altered precipitation cycles. The shadow would not be fixed in one exact location year-round. Because Earth's axis is tilted 23.5 degrees, the angle of sunlight shifts through the seasons. That means the shadow band would migrate slightly north and south over the course of a year. Some regions would spend months under deeper ring shadow conditions. Others would only experience it briefly. This seasonal shadow movement could create complex climate oscillations. Instead of uniform equatorial heating, you would have a dimmed belt slowly shifting with the sun's apparent motion. Over decades, that could cool equatorial oceans. Cooler equatorial waters influence global atmospheric circulation. Trade winds depend on temperature gradients between equator and subtropics. Change that gradient, and you change the winds. Even a moderate ring system could subtly rewire Earth's climate engine, and unlike a passing cloud or temporary eclipse, this shadow would be permanent, a structural feature of the planet. Every year, every day, a thin celestial band silently reducing the energy that powers weather, oceans, and life near the equator. If the rings were dense enough, they would not just cast shadows, they could cool the planet. Earth's climate is extremely sensitive to solar input. The total solar energy reaching the top of the atmosphere is about 1,361 watts per square meter. A global reduction of even 1% sustained over long periods is significant. During the Little Ice Age, global temperatures dropped by roughly 0.5 to 1 degree Celsius. That shift was linked to relatively small changes in solar activity and volcanic aerosols. Now imagine a permanent orbital structure reducing sunlight over key latitudes. If the rings blocked just 2 to 3% of solar radiation over the equatorial belt, that would reduce the energy absorbed by oceans in the region that drives global heat distribution. The equator is the thermal engine of Earth. Warm water rises, moves poleward, and redistributes heat. If that engine weakens, the entire circulation pattern shifts. Sea surface temperatures in the tropics could decline gradually. That would reduce evaporation rates. Less evaporation means less water vapor in the atmosphere. And since water vapor is a greenhouse gas, that could amplify cooling. This creates a feedback loop. Lower solar input leads to cooler oceans, leads to less evaporation, leads to weaker greenhouse effect, leads to further cooling. If sustained long enough, polar ice could expand. Expanding ice increases Earth's albedo, its reflectivity. Ice reflects more sunlight than ocean or land. More reflection means even less absorbed energy. That is another positive feedback loop. Under certain conditions, this chain reaction could push Earth toward a cooler global state. Not necessarily a snowball Earth scenario, but potentially a prolonged glacial period. However, the effect would depend heavily on ring thickness and opacity. A thin, sparse ring system might produce minimal climate impact, more visual than thermal. A thick, dense ring system could act like a partial solar shield. Some scientists have even proposed artificial ring-like structures or orbital shades as geoengineering tools to counteract global warming. The principle is similar. Block a small fraction of sunlight, lower average temperatures. But unlike a controlled artificial structure, natural rings would not be adjustable. They would shade specific latitudes more than others. The cooling would not be uniform. Equatorial cooling combined with continued polar sunlight during certain seasons could create unpredictable climate shifts. Storm tracks might shift, rain belts could move, desert zones might expand or contract. The stability of current agricultural regions would be uncertain. The idea of an ice age triggered by rings is not fantasy. It depends on density, duration, and feedback strength. A ringed Earth might not freeze solid, but it would not maintain the climate balance we evolved under. It would be a cooler, more complex planet. its atmosphere and oceans constantly negotiating with a permanent band of orbital shadow overhead. Earth is tilted 23.5 degrees. That tilt is why we have seasons. As the planet orbits the sun, different hemispheres receive more direct sunlight at different times of the year. Now add rings. Because rings sit in the equatorial plane, they are locked to that tilted axis. That means their shadow would not stay fixed in one narrow band year-round. It would shift north and south as the sun's apparent position changes. At the equinoxes, the sun sits directly above the equator. During those periods, the ring shadow would be strongest and most concentrated across equatorial regions. The shading effect would be at its maximum width. But during the solstices, when the sun is overhead in either the northern or southern hemisphere, the angle between sunlight and the ring plane changes. The shadow would migrate. In northern summer, parts of the northern hemisphere might experience reduced shading, while certain southern latitudes receive more. 6 months later, the pattern reverses. This would create a new kind of seasonal modulation layered on top of existing seasons. Today, seasons are primarily about axial tilt and hemisphere orientation. With rings, seasons would also include shifting orbital shadows. Some regions might experience dimmer summers, others might experience darker winters. The interplay between axial tilt and ring geometry would produce complex light patterns across the globe. The terminator between ring shadow and full sunlight would move gradually throughout the year. Agricultural cycles would need to adjust to these predictable but altered light regimes. Plants are sensitive not just to temperature but to photoperiod, the length and intensity of daylight. If certain regions receive slightly reduced sunlight every year during key growing months, crop yields could change significantly. The most dramatic seasonal effects would occur in subtropical latitudes, regions already sensitive to changes in sunlight intensity and precipitation. Monsoon systems depend heavily on land heating differences. If ring shadows alter heating rates during seasonal transitions, monsoon timing could shift. Over decades, these changes could reshape climate zones. Some regions might cool slightly year-round. Others might see exaggerated seasonal contrasts due to combined tilt and ring effects. The planet would not lose seasons, but they would become more complicated. Instead of a simple tilt-driven cycle, Earth would experience a layered system: axial tilt, orbital position, and ring shadow modulation. The sky would not just change color with the seasons. The brightness of the sun itself would subtly change depending on where you live. Rings would not just decorate the sky. They would become part of the seasonal rhythm of the planet. Photosynthesis is brutally simple. Light goes in, life comes out. Plants convert sunlight into chemical energy. That energy feeds everything else: forests, crops, plankton, oxygen production. All of it depends on stable solar input. Now introduce a permanent ring system that reduces sunlight over specific latitudes. Even a small drop in light intensity matters. Many plants operate near efficiency limits. Reduce incoming sunlight by 5% in certain regions, and growth rates decline. Reduce it by 10%, and entire ecosystems begin to shift. In equatorial rainforests, dense canopies already compete intensely for light. Slight dimming could slow biomass production. Some species adapted to intense direct sunlight might lose competitive advantage. Shade-tolerant plants could expand. Over decades, forest composition would change. Agriculture would be more sensitive. Crops are optimized for specific light conditions: corn, rice, wheat. They are tuned to photoperiod and intensity. A consistent reduction in peak sunlight during growing seasons could reduce yields. Farmers would adapt with selective breeding and greenhouse systems. But natural vegetation would respond more slowly. Marine ecosystems would also feel the impact. Phytoplankton in tropical oceans rely on sunlight penetrating surface waters. If ring shadows reduce light levels over equatorial oceans, plankton productivity could decline. That matters because phytoplankton form the base of the marine food chain and produce a significant portion of Earth's oxygen. Lower productivity in the tropics could ripple upward through fish populations, marine mammals, and global fisheries. But the impact would not be uniform. As ring shadows migrate seasonally, some regions would receive reduced sunlight at certain times of year, but not others. That variability could stress ecosystems. Some species might adapt to fluctuating light regimes, others might collapse. Now consider nocturnal ecosystems. Brighter nights from reflected ring light would reduce true darkness. Many species rely on darkness for hunting or protection. Predators that use low light to ambush prey might lose advantage. Prey species that hide in darkness might be exposed. Over time, behavior patterns would shift. More species might evolve twilight or low-light adaptations rather than strict nocturnal or diurnal behavior. Even human agriculture would adapt. Crops might need to shift latitudes. Regions previously ideal for certain plants might become marginal. Greenhouse farming might expand in areas affected by persistent shading. The biosphere would not collapse overnight, but it would reorganize. Life evolved under a rotating Earth with predictable light cycles and full solar exposure. Add rings, and you introduce a new environmental variable, a permanent orbital filter that subtly changes how much energy reaches the surface. And when you change energy flow, you change everything that depends on it. Earth's atmosphere runs on imbalance. Warm air rises near the equator. Cool air sinks near the poles. The planet rotates, and that rotation bends moving air into curved paths. That bending force, the Coriolis effect, is what creates trade winds, jet streams, cyclones. Now add rings. If rings reduce sunlight along equatorial regions even slightly, you weaken the primary heat source that drives atmospheric circulation. Today, the equator is the hottest part of the planet. That heat powers convection. Rising air near the equator moves poleward at high altitude, cools, sinks, and returns at the surface. This creates the Hadley cells, massive atmospheric circulation loops. If ring shadows cool the equatorial belt, the temperature gradient between equator and mid-latitudes changes, and atmospheric circulation depends entirely on gradients. Cool the equator enough, and you weaken upward convection. That weakens the Hadley circulation. That shifts the position of subtropical high-pressure zones. Trade winds could slow. Monsoons could change timing. Tropical storm formation might decrease if surface ocean temperatures drop below thresholds required for hurricane development. But here is where it gets complicated. The cooling would not be uniform. Some longitudes might receive more shading than others depending on seasonal alignment. That could create asymmetric heating patterns. Instead of a smooth temperature band around the equator, you could get uneven heating patches. Atmospheric instability thrives on uneven heating. Storm tracks might shift longitudinally. Regions that currently rely on predictable wind systems could see new weather extremes. Jet streams, which today are shaped by rotational forces and temperature differences, might migrate in latitude if tropical heating weakens. That affects mid-latitude weather patterns. Storm systems that normally track across North America or Europe could shift north or south. Rain belts might move. Deserts might expand or shrink depending on new circulation equilibria. Wind energy patterns would change too. Some regions might see weaker steady winds. Others could experience intensified pressure gradients along the edges of ring shadow zones. The atmosphere is not independent from the ocean. If equatorial oceans cool, evaporation drops. Less water vapor means less latent heat release in storm systems. That can weaken large-scale tropical convection but increase temperature contrasts elsewhere. The rings would not just dim sunlight, they would alter the engine that moves air across the planet. Wind patterns that have shaped ecosystems and human civilization for thousands of years could gradually shift. And because atmospheric systems are nonlinear, small changes in input can produce large changes in outcome. A ringed Earth would still have winds, but they would not follow the same rules we know today. The oceans do not move randomly, they move because of energy. Sunlight heats equatorial waters. Warm water expands, becomes less dense, and flows. Rotation bends those flows into vast gyres, massive circular currents in the Atlantic and Pacific. The Gulf Stream carries tropical heat toward Europe. The Kuroshio Current does the same for East Asia. These currents are not optional. They stabilize climate. Now introduce rings that permanently reduce solar input along the equatorial belt. You are not just dimming sunlight on land. You are dimming the thermal engine of the oceans. Equatorial oceans are the primary heat reservoirs of Earth. If rings lower sea surface temperatures even slightly in the tropics, evaporation declines. Less evaporation means less moisture entering the atmosphere. Less moisture means weaker latent heat transfer. That alone can weaken global heat redistribution. But the deeper impact lies in ocean density. Ocean circulation is driven by thermohaline processes, temperature and salinity differences. Warm, salty water sinks in certain regions, driving a planetary scale conveyor belt. If equatorial heating weakens, surface water in the tropics becomes cooler and denser than before. That changes sinking patterns. Deep water formation zones could shift. The Atlantic meridional overturning circulation, the system that includes the Gulf Stream, could slow or reorganize. A weakened Gulf Stream would cool Western Europe significantly. That is not speculation. Climate models show that even modest disruptions in ocean circulation can trigger regional cooling of several degrees Celsius. Meanwhile, polar regions accumulating expanded ice from ring-induced cooling would inject more fresh water into the oceans during melt cycles. Fresh water is less dense than salt water. That can further destabilize deep ocean sinking processes. Now imagine this instability playing out over centuries. Ocean currents do not shift instantly, but once altered, they can remain in new states for long periods. Marine ecosystems would feel the shock. Upwelling zones, regions where nutrient-rich deep water rises to the surface, depend on stable wind and current systems. If those systems shift, nutrient supply chains break. Phytoplankton productivity in key fisheries could decline sharply. Fish migration patterns would change. Entire marine food webs might reorganize. Coral reefs in slightly cooled tropical waters might initially benefit from lower thermal stress, unless reduced sunlight limits symbiotic algae growth. Polar ecosystems could expand into new areas as sea ice spreads. But none of this would be clean or gradual everywhere at once. Ocean circulation is nonlinear. Small changes in surface temperature can flip large systems into different modes. A ringed Earth might not freeze globally, but it could enter prolonged regional climate states, cooler tropics, colder Europe, altered monsoon-driven coastal currents in Asia and Africa. The oceans today buffer climate extremes. With rings overhead, that buffering system weakens. And when the oceans destabilize, the atmosphere follows. A ringed Earth would not just look different from space. Its entire internal heat redistribution engine would operate under new rules. And that means the climate we evolved under would no longer exist in its current form. Rings are not permanent. They look eternal when you see Saturn, but even Saturn's rings are temporary on cosmic timescales. Gravity never stops working. If Earth had rings, the particles would constantly interact with each other. Tiny collisions would exchange energy. Some fragments would drift slightly inward, others would drift outward. Over millions of years, that slow spreading would change the system. Particles orbiting just above Earth's atmosphere would experience faint atmospheric drag. Even at hundreds of kilometers altitude, the upper atmosphere is not empty. It is thin, but over long timescales, it matters. Small particles would gradually spiral downward. As they descend, they would heat from friction and burn up, just like meteors. That means Earth could experience continuous meteor showers, not from distant comets, but from its own rings. Not apocalyptic impacts, but constant streaks of light in the sky. If the ring system were dense, this could mean daily or even hourly visible meteor activity across certain latitudes. Larger fragments might survive atmospheric entry and reach the surface. Not extinction-level impacts, but a steady rain of small meteorites over geological time. Meanwhile, the outer edge of the ring system would slowly spread outward due to gravitational interactions. Once particles cross beyond the Roche limit, they are no longer prevented from clumping together. Gravity would begin pulling them into aggregates. Over time, those aggregates could form small moonlets, so a ringed Earth might not stay ringed forever. It could slowly transform. Rings could thin as material falls inward. Small moons could form as material drifts outward. Eventually, the system might stabilize into a reduced ring with one or more tiny moons orbiting beyond it. Or, if the total mass were small, the entire ring system might decay completely within tens of millions of years. That is short in planetary terms, but long compared to human civilization. From a human perspective, rings would feel permanent. From a cosmic perspective, they are transitional. They represent a phase between destruction and reassembly, a failed moon, or a future moon. A ringed Earth would not stay frozen in that state forever. It would evolve, particles falling, fragments merging, gravity slowly reorganizing the debris, until one day, the sky clears again, and the planet returns to being just a sphere. But only after millions of years under a luminous orbital scar. If Earth had rings, space would become far more dangerous. Right now, satellites orbit in relatively predictable paths. Low Earth orbit sits between roughly 160 and 2,000 kilometers above the surface. Geostationary orbit sits at about 35,786 kilometers. Between these regions, space is mostly empty except for artificial debris. Add a ring system, and suddenly there is a dense, high-speed debris field encircling the planet along the equator. Ring particles would orbit at several kilometers per second. Even a pebble-sized fragment at orbital velocity carries enormous kinetic energy. Anything crossing the ring plane would risk catastrophic impact. Most satellites use specific orbital inclinations. Many Earth-observing satellites operate in polar or near-polar orbits, so they can scan the entire surface as the planet rotates beneath them. Those polar orbits would intersect the ring plane twice every orbit. If the ring density were significant, each crossing would carry collision risk. Satellite lifespans would drop dramatically. Engineers might be forced to design orbital corridors that avoid the densest parts of the ring system. Perhaps rings would develop gaps similar to Saturn's, shaped by gravitational interactions. Satellites could exploit those gaps, but any launch from equatorial spaceports would face a direct challenge. Rockets leaving Earth must pass through orbital altitudes. If they launched along trajectories that intersect the ring plane at low altitude, they could collide with debris during ascent. Launch windows would become restricted. Trajectories would need precise timing to avoid dense ring segments. Space travel would not stop, but it would become far more complex and risky. Low Earth orbit infrastructure, communication satellites, weather satellites, space stations would need heavy shielding or entirely new orbital strategies. Perhaps humanity would rely more on polar orbits carefully aligned to minimize intersection with ring material. Or perhaps launches would shift to high latitudes where initial trajectories avoid the densest equatorial debris zones. The presence of rings would also change how Earth looks from space. Astronauts in orbit would see a massive flat disk slicing across the planet's equator. But they would also see constant streams of particles glinting in sunlight. Space would no longer feel empty around Earth. It would feel crowded. A ringed Earth would not just alter the sky from below. It would fundamentally reshape how humanity interacts with space. Orbital mechanics would remain the same, but orbital safety would never be the same again. The moon would not ignore the rings. Right now, the moon stabilizes Earth's axial tilt and influences ocean tides. Its gravity shapes long-term planetary stability. If Earth suddenly gained a ring system, the moon would begin interacting with it immediately. Gravitational resonance would become the key factor. Every object orbiting Earth has a specific orbital period. If ring particles orbit at certain distances, their motion could synchronize with the moon's orbit in predictable ratios. These resonances would either stabilize parts of the ring or carve gaps into it. This is exactly what happens in Saturn's rings. Small moons embedded in Saturn's ring system create gaps, waves, and density patterns through gravitational interactions. The Cassini division exists partly because of resonance with Saturn's moon Mimas. Earth's moon is far more massive relative to Earth than Saturn's small shepherd moons are relative to Saturn. That means its influence would be strong. Over time, the moon's gravity would create density waves in the ring. Spiral patterns might form. Regions of higher particle concentration could appear. Other regions could be cleared out entirely. If parts of the ring drift too far outward, approaching orbital distances influenced strongly by the moon, gravitational disturbances could eject particles from stable orbits. Some debris might be flung inward toward Earth. Some might be pushed outward beyond the Roche limit, where it could begin clumping into small moonlets. The moon could also gradually destabilize the ring system over millions of years. Because the moon is slowly moving away from Earth, about 3.8 centimeters per year, the gravitational relationship between the moon and the rings would evolve over time. That means the ring structure would not remain static. It would be sculpted continuously. The moon might act like a cosmic sculptor, carving lanes and patterns into the debris disk. Visually, this would create subtle banding and divisions visible from Earth's surface. The ring would not be a uniform sheet. It would show structure, brighter and darker segments shaped by lunar gravity. There is also the tidal interaction factor. The same tidal forces that slow Earth's rotation and push the moon outward would influence ring particles. Angular momentum transfer between Earth, the moon, and the rings would gradually alter orbital distances. In extreme cases, if the ring mass were significant, there could be measurable feedback effects on the moon's orbital evolution. The Earth-Moon system is delicate. Add a ring, and you add another moving component to that gravitational dance. The moon would not destroy the rings instantly, but it would shape them. Over millions of years, it could determine whether the ring system remains stable, fragments further, or slowly transforms into a new configuration. A ringed Earth would not orbit alone. It would orbit with a moon constantly pulling, carving, and reshaping the debris that once tried to become a satellite. If Earth had rings, the sky would not just change physically, it would change psychologically. For all of human history, the sky has been open, vast, empty except for stars, planets, the sun, and the moon. Every civilization built its myths under that open dome. Now imagine growing up under a permanent celestial structure stretching from horizon to horizon. At the equator, the rings would dominate the sky every day of your life. Children would never see a sky without that luminous band overhead. It would not be special. It would be normal. But it would shape everything. Calendars might track subtle brightness, changes in the rings across seasons. Religious symbolism would inevitably center around the celestial arc. It would appear as a cosmic boundary, a divide between above and beyond. Architecture might align with it. Ancient temples today align with solstices and equinoxes. In a ringed world, buildings could align with ring angles, shadow crossings, or seasonal ring illumination events. Art would reflect it. Poetry would reference it. Navigation would use it. In mid-latitudes, where the ring cuts diagonally across the sky, people might associate it with direction, a permanent line marking celestial orientation. At the poles, the thin glowing circle around the horizon would feel like a boundary, a ring marking the edge of the world. Psychologically, the sky would no longer feel infinite. Today, when you look up, you see depth, stars fading into darkness, a sense of vastness. With rings overhead, part of that depth is blocked. a structural reminder that Earth is wrapped in orbiting debris. That changes how humans perceive their place in space. The moon today inspires imagination because it is singular. A ring would feel more overwhelming, larger, more dominant. Space agencies might face different public perceptions of space exploration. With visible debris encircling Earth, space would look more cluttered, less empty. Culturally, eclipses might feel different too. The rings interacting with sunlight could create complex optical phenomena, halos, arcs, diffused light patterns never seen in our current sky. And at night, when the ring glows faintly above you, there would be no true emptiness. The Milky Way might be partially obscured near the equator. Deep sky observations would feel framed by the ring's presence. A ringed Earth would not just alter physics and climate, it would alter identity. Humanity evolved under an open sky. Under rings, the sky becomes structured, defined, encircled, and over generations, people would not ask what the sky looked like before. They would assume it had always been this way. If Earth had rings, they would not remain perfectly smooth. Gravity hates uniformity. Even if the ring system formed as a relatively even disk of debris, over time it would develop structure, bands, gaps, density waves, and the main sculptor would be resonance. Every particle in the ring orbits Earth at a specific speed depending on its distance. Closer particles orbit faster, farther particles orbit slower. That difference alone creates shear and internal motion within the disk. Now introduce the moon. If a ring particle's orbital period matches a simple ratio of the moon's orbital period, say 2:1 or 3:2, it experiences repeated gravitational tugs at the same position in its orbit. Repeated tugs matter. Over time, those resonances either push particles into more stable orbits or eject them from certain zones. That is how gaps form. In Saturn's rings, moons like Mimas carve out entire divisions through resonance alone. Earth's moon is far more massive relative to Earth than Mimas is to Saturn. Its influence would be stronger. You would not get a single uniform glowing band. You would get structure. From the surface, that structure might appear as subtle brightness variations, thin dark lanes, brighter arcs, maybe even visible rippling patterns if the density contrast were strong enough. There could be shepherd effects as well. If fragments at the outer edge of the ring began clumping together just beyond the Roche limit, small moonlets could form. Those moonlets would then gravitationally herd nearby particles, sharpening edges and maintaining distinct boundaries. The result would be a dynamic ring system, constantly reshaped. Collisions between particles would grind material into finer dust over time. Radiation pressure from the sun would slowly push tiny grains outward. Larger fragments would dominate the remaining structure. There is also orbital precession to consider. Earth is not perfectly spherical. Its slight equatorial bulge affects orbital motion. Ring particles would experience tiny variations in gravitational pull depending on longitude. Over long periods, this could twist and warp sections of the ring. And then there is the sun's gravity. Although Earth's gravity dominates close-in debris, the sun still exerts influence. Solar tidal forces could introduce subtle distortions, especially in the outer ring regions. All of this means the ring would never be static. It would evolve. Waves would ripple through it. Gaps would widen or narrow. Bright zones would shift. Over thousands of years, careful observers could track slow structural changes in the ring's appearance. A ringed Earth would not be a frozen snapshot. It would be a gravitational laboratory visible in the sky, a constant reminder that orbit is not calm. It is tension balanced in motion, and that balance never stays perfectly still. If Earth had rings, they would not just stay safely in orbit forever. Gravity is stable, but it is not perfect. Over time, parts of the ring would decay. Particles near the inner edge, closest to Earth, would slowly lose energy. Tiny collisions between particles generate heat and redistribute momentum. Some fragments would drift inward, entering lower and lower orbits. Eventually, they would cross into denser layers of the upper atmosphere, and then they would fall, not as a single catastrophic event, but as a constant rain. Every day, fragments would burn up, streaking across the sky as meteors. In a dense ring system, meteor activity could become routine. Instead of rare meteor showers tied to comet debris, Earth might experience nightly streaks of falling material, especially near the equator where the ring plane sits directly overhead. The size of incoming fragments would vary. Most would be tiny, dust grains, pebble-sized particles, vaporizing harmlessly in the atmosphere. But occasionally, larger fragments could survive partial descent and reach the surface. Not extinction-level impacts, but frequent small meteorite falls. Over centuries, certain regions might accumulate measurable amounts of extraterrestrial rock. The sky would often glow with faint trails of burning debris. Auroras would not be the only atmospheric light phenomena. There would be a subtle, persistent reminder that the rings are not permanent. Now consider what happens if a larger fragment destabilizes. If collisions inside the ring knock a meter-sized or larger object into a decaying orbit, it could survive atmospheric entry long enough to strike the surface. Impact frequency would increase compared to present-day conditions. Earth today is relatively protected from constant bombardment. With rings overhead, Earth becomes its own source of impacts. There is another consequence. As ring material falls inward, the total mass of the ring decreases. The system thins. Brightness declines slowly over millions of years. The once dominant band across the sky would gradually fade. At the same time, outer ring material drifting beyond the Roche limit might begin clumping into small moonlets. So while the inner edge decays, the outer edge might birth new objects. The ring system would slowly transform from a solid, bright structure to a thinner band, to scattered fragments, until eventually perhaps nothing remains but a few small moons and faint dust. From a human perspective, this decay would be imperceptibly slow. But on geological timescales, rings are temporary. They are not a final state. They are a phase, a transitional scar left by destruction. And eventually, gravity either pulls them down or builds something new from their remains. If Earth had rings, space exploration would never look the same. Right now, launching a rocket is a matter of timing, trajectory, and fuel. Engineers calculate a path through relatively empty orbital space. The biggest hazards are atmospheric stress and artificial debris. With rings, that empty space would no longer be empty. The ring plane would be filled with billions of orbiting particles traveling at several kilometers per second. Even a centimeter-sized fragment at orbital velocity carries the energy of an explosive projectile. A rocket leaving the equator, which is ideal today because it provides extra rotational speed, would face an immediate problem. It would have to cross the ring plane. If the ring density were high, that crossing could be lethal to the vehicle. One impact with a fist-sized fragment at orbital speed would be catastrophic. Launch windows would need precise timing. Perhaps rockets would launch at specific angles to avoid the densest parts of the ring. Perhaps the ring would contain gaps created by lunar resonance, corridors where debris density is lower. But those corridors would not be static. They would shift slowly over time. Low Earth orbit infrastructure would also be affected. Satellites in equatorial orbits would operate within or near the ring plane. They would require heavy shielding or drastically shortened lifespans. Polar orbit satellites used for Earth observation would intersect the ring plane twice every orbit. Each crossing increases collision risk. Space stations could not safely remain in equatorial orbit without significant protective design. Human spaceflight would require entirely new strategies. Launch sites might move toward higher latitudes to reduce direct ring plane intersections during ascent. Spacecraft might use steeper launch angles to clear the densest debris zones quickly. Interplanetary missions would need to consider ring avoidance when departing Earth. The ring system would effectively create a hazardous equatorial debris belt. From space, Earth would look majestic. From an engineering perspective, it would look dangerous. The presence of rings would not end space exploration, but it would complicate it dramatically. Earth would no longer be surrounded by mostly empty orbital space. It would be encircled by a natural debris field, a reminder that beauty and danger in the universe often share the same structure. From space, Earth would stop looking like a blue marble. It would look engineered. Right now, when astronauts orbit Earth, they see a sphere, oceans, clouds, continents, clean, isolated against black space. Add rings, and that simplicity vanishes. From low Earth orbit, the rings would appear enormous. If you were aboard a space station near the equator, you would see a massive flat disk cutting across the horizon. It would not be a thin halo. It would be a geometric plane stretching outward tens of thousands of kilometers. You would see layers within it, dense bands, gaps carved by resonance, perhaps faint spiral density waves rippling through the debris. Sunlight would scatter differently depending on viewing angle. At certain angles, the rings would glow brightly, almost white or silver. At others, they would appear darker, almost invisible against space. When backlit by the sun, the rings could appear translucent, a thin veil of particles illuminated from behind. When viewed in shadow, they might appear as a dark silhouette slicing across the planet. From geostationary orbit, 35,786 kilometers above Earth, you would see the full structure clearly. Earth in the center, a wide, flat disk extending outward like a cosmic vinyl record. The scale would be shocking. The rings could extend far beyond the altitude of many satellites. Entire classes of orbit would sit inside or outside the ring plane depending on inclination. Now imagine viewing Earth from deep space. From the distance of the Moon, Earth would resemble a miniature Saturn, a blue sphere wrapped in a gray or silver band. But unlike Saturn's bright icy rings, Earth's rings, likely rocky, would have a subtler tone. less brilliant white, more metallic gray with warm highlights. The contrast between deep blue oceans and muted ring debris would create a striking image. From Mars, Earth would no longer appear as just a bright star-like dot. Under powerful telescopes, the ring system might be detectable as a slight elongation or brightness asymmetry. Astronomers observing Earth from afar would classify it differently. A ringed terrestrial planet. Rare. Unusual. In exoplanet studies, rings around rocky planets are not commonly observed, partly because detecting them is difficult. If Earth had rings, its light curve during transits would change. The ring system would block additional starlight. Observers from distant star systems might detect Earth more easily. Ironically, rings might make Earth more visible to the cosmos. Back closer to home, solar eclipses would change. When the moon passes in front of the sun, observers on Earth see the sun's corona. With rings present, eclipse-light interactions would become more complex. The ring particles might catch and scatter sunlight differently during partial phases. The sky from orbit during sunrise and sunset would become even more dramatic. Astronauts would see Earth's shadow climbing up the ring plane, a massive curved shadow slicing across the disk. You would literally watch Earth's night sweep across the rings. That is something no current astronaut experiences. Earth today feels spherical and clean from space. A ringed Earth would feel layered, structured, encircled. It would look less like a lone world and more like a system, planet and debris locked together in orbit. From space, the rings would not just decorate Earth, they would redefine its silhouette. If Earth had rings, they would not just change physics or climate, they would change civilization. From the very first humans who looked up at the sky, the rings would be there, permanent, immovable, a celestial structure dominating half the heavens. Religion would be different. Instead of a single moon waxing and waning, people would see a vast band stretching across the sky every night. It would feel intentional, designed, too geometric to ignore. Ancient myths would likely describe it as a boundary between worlds, a bridge to the gods, a celestial scar from a cosmic battle. Entire belief systems might form around the idea that Earth is encircled for protection or imprisonment. Calendars would incorporate ring brightness and seasonal shadow shifts. Harvest festivals might align with times when the rings cast minimal shadow. Ceremonies could mark moments when the rings glow brightest at sunset. Navigation would change. Before compasses, humans navigated by stars. With rings present, especially near the equator, part of the sky would be partially obscured. Navigators would learn to use the ring itself as a directional reference. It would act like a permanent celestial equator marker. Architecture would reflect it. Temples and monuments today align with solstices and equinoxes. In a ringed world, structures might align with the angle of the ring in the sky. Entire cities might orient toward the celestial band. Art would be dominated by it. Paintings, sculptures, poetry, all infused with the presence of a sky that is never empty. Now consider science. Astronomy would develop differently. Equatorial observatories would struggle to observe deep space in the direction blocked by the ring. Telescopes would be built at higher latitudes to avoid interference. The ring's structure would become one of the earliest scientific curiosities. ancient astronomers would track subtle changes in brightness or structure over centuries. It might accelerate humanity's understanding of orbital mechanics earlier in history, because the sky would visibly demonstrate gravity in action. Psychologically, the presence of rings might make humanity feel less isolated in space. Today, when we look up, we see emptiness and distant stars. In a ringed world, we would see orbiting matter constantly, a reminder that Earth is part of a dynamic system, not a static rock. Children would grow up assuming all planets have rings. When they eventually discovered that most do not, Earth would feel rare, special, or damaged. There is also a darker psychological possibility. A permanent debris field overhead might feel like a reminder of past destruction, a failed moon, a cosmic catastrophe frozen in orbit. Some cultures might interpret it as a wound, others as a crown. But one thing is certain: human identity would be shaped by it. We evolved under an open sky. A ringed Earth would raise generations under a sky that is structured, divided, encircled. And over thousands of years, no one would remember a time when the heavens were clear. If Earth had rings, they would not last forever. Nothing in orbit is permanent without constant balance. Ring systems are fragile structures held together by gravity and motion. Over millions of years, slow processes would begin dismantling them. The first force working against the rings would be collision. Ring particles constantly collide. Even gentle impacts change velocity slightly. Those tiny changes accumulate. Some particles gain energy and drift outward. Others lose energy and spiral inward. This process is called viscous spreading. Over time, the ring widens. The inner edge moves closer to Earth. The outer edge moves farther away. The inner material eventually encounters atmospheric drag. Even at very high altitudes, Earth's atmosphere is not a hard boundary. It fades gradually into space. Small particles drifting too low would experience resistance. They would heat. They would burn. They would fall as meteors. The outer material, meanwhile, approaches the Roche limit boundary. Once particles move beyond that gravitational threshold, they are no longer prevented from clumping together. And gravity does what gravity always does. It pulls fragments into aggregates. Small moonlets could begin forming beyond the ring's outer edge. So the ring would slowly lose mass in two directions: inward through decay, outward through moon formation. There is also radiation pressure. Sunlight exerts force, tiny but real. On microscopic dust particles, radiation pressure can slowly push material outward over long time scales. Solar-wind interactions could also affect charged dust grains, altering their orbits gradually. If the ring were composed largely of rocky debris, its reflectivity would be lower than Saturn's icy rings. That means it would absorb more heat, potentially accelerating fragmentation into finer dust. Over millions of years, the ring would thin. Brightness would decline. The once dominant band across the sky would fade slowly. Humans alive during its existence would never notice the change. It would be far too gradual. But geological records might show increased meteor deposition during certain eras. Eventually, one of two outcomes would occur. Either the ring decays almost completely, leaving behind perhaps a few small moons, or enough mass migrates outward to form a more stable satellite beyond the Roche limit. In that case, Earth could gain a second moon, a moon born from destruction. A ring system is not an endpoint, it is a transition, a moment between catastrophic breakup and gravitational reassembly. And over cosmic timescales, gravity always wins. It either builds something new or clears the sky entirely. In the end, a ringed Earth would not stay ringed forever. It would evolve. If the ring system were massive and stable enough, it could persist for tens of millions of years, long enough to reshape climate, long enough to influence evolution, long enough to redefine human civilization. But gravity does not allow static beauty. Over time, the inner edge of the ring would continue to decay. Particles would burn in the atmosphere. Meteor activity would slowly decline as the ring thins. The outer edge would drift outward. Beyond the Roche limit, fragments would begin sticking together. Small moonlets would form. Some might collide and merge. Eventually, one larger body could dominate. A second moon. Not as large as our current moon, unless the original ring mass were enormous, but perhaps a small companion orbiting beyond the ring's former boundary. If that happens, Earth transitions again, from a ringed planet to a two-moon world. The sky would change once more. The glowing band fades. In its place, a new satellite slowly grows brighter over millions of years. Alternatively, if the total ring mass were modest, it might simply disappear. Particles spiral inward, moonlets never fully form. The sky gradually clears. Generations far in the future might notice that the once bright celestial band is thinner than historical records describe. Eventually, it becomes faint, then barely visible, then gone, leaving behind only myths and geological traces of increased meteor deposition in ancient strata. From space, Earth returns to a clean silhouette. No disk, no encircling scar. Just a blue sphere and its moon. The ring phase would be remembered, if intelligent observers still existed, as a temporary chapter. A visible reminder that planets are not static objects. They are systems, shaped by impact, by gravity, by slow orbital drift. A ringed Earth would be beautiful, but it would also be transitional, because in the long run, orbiting debris either becomes a moon or becomes dust.